violent nuclear furnace spews forth millions of tons of energy every second, the equivalent of some 500 billion horsepower.
Well, throughout history, the basic problem in determining the source of the sun's energy has been to find a source that's able to produce that much energy for that long a time without consuming most of the sun in the process. Now, of course, we're able to look at sunlight with solar telescopes like these, but understanding the source of that light is another matter entirely. We need to have a theory which explains and agrees with the evidence. Now, the sun has been shining for about 4.5 billion years, and that means that any theory, any explanation of the sun's energy is going to have to keep the sun shining for that long a time at least. Now, there have been lots of ideas proposed to explain how the sun shines, but most of them have failed, largely because they can't keep the sun shining long enough. Well, for instance, in the 5th century BC, Socrates simply proposed that the sun was a red-hot stone, cool off much too fast, so that doesn't work. At about the same time, Pythagoras suggested that the sun shines by reflected light. It doesn't give off light of its own, he said. Well, this simply moves the problem of the energy of the sun elsewhere, to the so-called Great Central Fire, which was always on the opposite side of the Earth. Or you could imagine that the sun is just a lump of burning coal. Well, you've got 2 × 10 to the 33rd grams of sun to burn at a rate of 4 × 10 to the 33rd ergs per second. That's just the energy output of the sun. And doing that with coal, burning coal at that rate, only allows the sun to last a few thousand years. So that explanation obviously can't work either. But in 1905, Albert Einstein was able to suggest a relationship between mass and energy, E equals mc squared. And this would permit a small amount of matter to produce a great amount of energy. Well, in 1938, Hans Bethe and Charles Critchfield were able to show that thermonuclear fusion could make E equals mc squared work. They were able to find a reaction that could explain what we see, the evidence, in terms of the known laws of physics. Since 1938, we've refined the reactions, but we believe the basics are still the same. Hydrogen is transformed in a process which produces great amounts of energy.
Spectrogram of the sun shows the 2 simplest and lightest elements, hydrogen and helium. The word helium comes from the Greek word helios, which means sun. Helium was discovered on the sun before it was found on Earth. A slightly more complex atom than hydrogen, helium has 2 electrons, 2 protons, and 2 particles called neutrons. A neutron has no electrical charge and can be thought of as an electron and a proton combined. With the high temperature and pressure on the sun, 4 hydrogen atoms can fuse to construct 1 helium atom. The net effect is fusion, like separate drops of water becoming 1 drop. Although it is much more complicated than shown here, all the particles in the 4 hydrogen atoms fuse to form 1 helium atom. To see if the helium atom has the same mass as the 4 hydrogen atoms combined, a cash register is used to keep track of the atomic units of mass. First, there were 4 hydrogen atoms, then 1 helium. The fusion resulted in the loss of which corresponded to a large amount of energy. Physicists now know that whenever energy is given off, there is a corresponding loss of mass. And whenever a nuclear rearrangement results in a loss of mass, energy is given off. Each second, 4 million metric tons of the sun's mass is converted into tremendous amounts of energy, a small portion of which reaches the Earth. The sun is so large that it will take millions of years before the Earth will feel the effect of the sun's reduced size. The energy produced by nuclear fusion in the sun is used by plants in the process of photosynthesis. When the sun's energy is stored in plants and fossil fuels, only electrons, not nuclei, are affected. The sun's energy changes the orbit of the electron. The nucleus, however, is not affected. The atom gives up the acquired energy when the electron jumps back to its original orbit. Also, in chemical burning, the nucleus is not affected, only the electrons. However, energy can be released from the nucleus through nuclear fission. This is a model of the most complex atom found in nature, the uranium atom. Scientists have discovered that if the nucleus is bombarded with a neutron, it splits the atom apart, freeing other neutrons to split still more nuclei. This is known as a chain reaction. The splitting of a nucleus is called nuclear fission. The uranium-235 atom is chosen to demonstrate the atomic units. It usually splits into two parts, with masses almost alike. This is the sum of the units of the two new elements. So with each new fission, mass is converted into energy and particles are released to continue the process. Until now, nearly all of the energy used on Earth has come from the burning of limited sources of fossil fuels, a process involving the rearrangement of electrons. The energy stored in oil, coal, and natural gas originally came from the sun. Stored from it is now rapidly being consumed. Power plants across the country have begun utilizing the techniques of nuclear fission to harness energy. The byproducts of nuclear fission, though, can be very hazardous if not disposed of properly. Nuclear fission involves the splitting of the atom's nucleus. This was demonstrated in the blast of the atom bomb. Superseding the atom bomb was the hydrogen bomb, utilizing nuclear fusion, an even more powerful and efficient form of energy than nuclear fission. Through nuclear fusion, and because of its tremendous size, the sun releases energy every second, equivalent to the simultaneous blast of billions of the world's largest hydrogen bombs. Now scientists are working on obtaining energy from the controlled fusion of atoms. Controlled nuclear fusion and eventual fusion reactors are still the subject of intense research. Controlled thermonuclear energy becomes practical. It will have the advantage that it produces less dangerous byproducts than fission, and its fuel, hydrogen, is available in abundant quantities in the sea. The release of energy from the nucleus results in an immense power to create or destroy.
There's an interesting paradox here. Thermonuclear fusion, the transformation of hydrogen to helium, produces gamma ray light, not visible light. Yet the sun obviously produces visible light. That's how we see it. Well, where does that light come from?
When we look at the sun, a couple of apparent paradoxes come to mind. One is, what do we actually see when we look at the sun? Because the sun is a ball of gas, and gases are invisible. In fact, I have some gas in my hand. You can't see anything. Well, it turns out when we look at the sun, we don't actually see the physical star. We see the light that is being given off by the sun. Of course, that presents another paradox because the sun doesn't produce any light. The sun produces highly energetic gamma rays. And so where does the light come from that we observe coming from the sun? The energy in the sun is produced way down in the core, way down in the central regions of the sun, where the temperatures and pressures are high enough to sustain the thermonuclear reactions that convert hydrogen into helium and give off this tremendous amount of energy. And this energy that's given off is in the gamma photons. And these gamma photons that are given off in the core of the sun want to get to the surface of the sun, because it's one of the final laws of nature that says that energy always flows from a hot region to a cooler region. And so let's look at what happens when one of these gamma photons is given off in the core of the sun, and it starts on this long journey, roughly 500,000 kilometers up to the surface. Well, the gamma photon travels at the speed of light. On the average, it only gets about a centimeter before it encounters an atom and it gets absorbed. And then that gamma photon will get re-emitted in another direction, perhaps as two other photons of less energy. And if we follow one of those, it will travel a centimeter or so. It'll get absorbed, re-emitted in another direction, get absorbed, perhaps two or three will get re-emitted. And so this energy sort of struggles to work its way out of the sun, and in the process, the photons carry less and less energy of each individual photon. And so you start out with gamma photons, they're slightly degraded to become X-ray photons, and then ultraviolet photons, and finally by the time they reach the surface of the sun, they've lost so much energy that they are visible photons. Well, how long does this process take? How long does it take the energy to get from the core to the surface? If a photon could travel unimpeded over this 500,000 kilometers or so, it would make it in about 2 seconds. But absorption and emission, the mathematicians call a random walk, turns out it takes about 1,000,000 years on the average to get out of the sun. And so the light that we see coming from the sun today is the result of thermonuclear processes that occurred way down in the core of the sun over 1,000,000 years ago.
Every second in the sun's core, at a temperature of about 15 million degrees Kelvin, a mass of 600 million metric tons of hydrogen is transformed into 596 million metric tons of helium and 4 million metric tons of energy. After hundreds of thousands of years of zigzag absorption and re-emission, the radiant energy reaches the surface, where most of it is visible from the Earth as sunlight 8 minutes later. However much is known about the sun, many puzzles still remain. For example, as the sun's atmosphere rotates, the period of rotation progressively increases from 25 days at the solar equator to about 33 days at the poles. Recently, some changes in these rates of rotation have been noted at Kitt Peak National Observatory.
We also observe solar rotation as part of our program here at Kitt Peak. Last year, Robert Howard at Mount Wilson announced that he had found that on the basis of some 10 years of observation that the sun had sped up slightly in its apparent rotation rate. I've been working with a young man, Tom Duvall, and we also have observations going back to 1966, in fact, about 11 years of observation. And indeed, we do verify Howard's finding that the sun appears to have sped up a little bit over this length of time. We simply do not know what would cause the rotation to vary. The whole sun, of course, cannot be varying. It must be only a skin, a layer, a very thin layer, because you just can't change the amount of momentum of a huge body such as the sun. I suppose it could be related somehow to the coupling between the magnetic fields inside the sun, which may rotate at a different rate than the surface as we see it, and the surface features. Sometimes that coupling may be stronger than other times.
Energy is constantly being transferred on Earth, in space, on the sun. 3 methods of transferring energy from one given point to another are convection, conduction, and radiation. Convection is the method in which material circulates between hot and cool regions, transferring thermal energy to the cool region. Lava flowing from a volcano, or even tomato soup boiling on the stove. Once a pattern of circulation is stabilized, convection can be very efficient in transporting energy. Heat also moves by conduction. These toy soldiers are held to the steel rod by wax. When the end of the rod is heated, the heat seems to move slowly towards the end. With conduction and convection, heat moves slowly from molecule to molecule. However, another important way heat is transported is through radiation. An electrical heat element is placed at the focal point of this reflector. 1 meter away, another reflector focuses on a wire holder. Several centimeters away, the unfocused heat is not very intense. The focal point is 1 meter away. This is the path of the radiation. Because heat moves by radiation, it can be focused in the same way as X-rays, radio, and light waves. Of the 3 processes of energy transfer, 2 appear to be very important on the sun. Radiation transfers energy from the core. From there, convection appears to take over as hot gases transfer heat the rest of the way to the photosphere. There, the turbulent bubbling. A small fraction of this energy on the sun passes freely out into space in the form of neutrinos, which are massless subatomic particles created by nuclear reactions. By detecting solar neutrinos, astronomers hope to gain first-hand information about the hydrogen-burning core of the sun. Information arrived at partly by experiments and partly by theoretical studies.
The problem in studying any theoretical model of the sun is that we cannot see below the surface. The surface of the sun is opaque. When we try and look into it, our looking agent, namely light, is blocked where the material becomes opaque. The neutrinos, on the other hand, can stream freely out through the sun. We describe those with a little Greek letter nu. The sun is completely transparent to neutrinos, and any neutrino formed in the center of the sun takes a straight line from its point of formation right out to the surface, and therefore provides us with the opportunity of, in effect, looking into the very center of the sun and testing to see whether the nuclear reactions that we calculate in our theoretical models are at all related to what happens in the sun. They're very direct tests of the solar models. And unfortunately, we calculate 2 to 3 times as many neutrinos should be emitted from the center of the sun as are being detected by Dr. Ray National Laboratories.
One of the subatomic particles traveling unhindered from the center of the sun is the neutrino. With a notorious reputation for reacting with practically nothing, these neutrinos are very hard to detect. In an attempt to count these elusive particles, nuclear scientists have built a specially designed solar telescope and buried it in a gold mine 5,000 feet underground in the Black Hills of South Dakota. Not a conventional telescope with lenses and highly polished mirrors, but a large, crude steel tank filled with 100,000 gallons of dry cleaning fluid. 4 or 5 times a year, these nuclear astronomers come to the home state gold mine and blow helium gas through the tank to churn up the cleaning fluid. Helium, the scientists draw out any radioactive atoms of argon that may have been formed as the chlorine in the fluid absorbed neutrinos. In the laboratory, the minutely small sample of argon gas is chemically purified and separated from other rare gases. It's carefully shunted into a very small counter. The quantity of argon present indirectly indicates the number of neutrinos which pass through the tank. So far, the neutrinos measured have not matched the scientists' predictions.
The cause for this discrepancy between observed and predicted neutrino flux is something that we really don't understand at the present time. Presently, I'm trying to evaluate the uncertainties in the theoretical models to see whether there's a possibility that it's the combination of a lot of uncertainties that go into building one of these models, or whether there's something fundamentally wrong with the physics. The general suspicion is that there's something fundamentally wrong with the physics that we use in calculating a theoretical model. The sun did not form as a chemically homogeneous body when it first became a star. Maybe there were layers which had different composition.
In science, when we perform an experiment and we get the results that we had anticipated, that's comforting to the scientist. That tells us that we understand the system probably, we did the experiment properly, we can write a paper, put the problem to bed, so to speak. But when we perform an experiment and the results are unanticipated, they're different than what our theory has predicted, that's when it gets exciting, because that means we have the potential to learn something new. That means we don't understand the system and there's more to be understood with further study. And I think that these unanticipated results also are the motivation for further experimentation. Good example of this has been Ray Davis's experiments with his neutrino telescope in trying to detect these neutrinos from the sun. The results were totally unanticipated, and there's been a great resurgence in interest in the sun in the last few years, in part, I think, because of Davis's results. As far as the neutrinos themselves are concerned, there's a proposal, it's kind of interesting, to build another type of neutrino detector. This one would use the element gallium, and if the neutrinos are there and they interact with gallium, a little bit of it would be converted into germanium. Trouble is, this experiment requires something like, and the world production of gallium is only about 7 tons a year. So whether that experiment will ever be performed is questionable.
The missing solar neutrinos are a real fly in the ointment right now as far as our theories of energy production are concerned. But when we do finally sort that problem out, the solution will tell us something new and useful about the nearest star, our sun. And it's like the unresolved problems we face with the cycles of solar activity and their possible relationships with the climate of the Earth. This case of the missing solar neutrinos really is important. There's a spectacular source of energy up there shining down on us every day, and we've barely begun to take advantage of it. We have used the sun, and we do use it now. We use it to grow our food. In the past, we've done things like tell time with the sundial, like this. But we really haven't taken full advantage of what the sun has to offer. And in the future, we're going to have to do that. And if we're going to succeed, we're going to have to figure out how the sun works.
For centuries, many questions concerning how the sun works have remained unsolved. Even with sophisticated observational instruments, increased knowledge, and intensive experiments, many of the questions remain today. In fact, with increased knowledge come further mysteries. Intrigued by these mysteries and the potential they involve, scientists continue to explore the sun.